Hi everybody, welcome back to Super Awesome Calculus. I'm Augie Kennedy, and today we're going to be talking about volumes, more specifically volumes of revolution. But before that, let's go back to the last lecture about areas between curves. I gave you an exercise to do, and the big problem that I gave you was I asked you to find the area between the curves y equals square root of x, y equals x over 2, and x equals 9. So, let's go ahead and let's write these. Y equals square root of x, y equals x over 2, x equals 9. Alright, well the first thing we want to do, as I mentioned, is we want to go over where the points of intersection are. That's a very important question. And the points are going to intersect when the y values are the same. So, we're going to have to look at x, or square root of x, and we're going to have to look at x over 2. So, square root of x equals x over 2. Well, the first thing we do is we square the square root of x. We don't want to deal with that. So, square root of x squared is x. X over 2 squared is x squared over 4. So, x minus x squared over 4 equals 0. Or x times 1 minus x over 4 equals 0, which, did I do that right? I may have done that right. I may have done that wrong, actually. No, it should still come out. Yeah, it still comes out. X is going to equal 0 and 4. So we know that the curves are going to intersect at 0 and 4. Sorry. Okay. So 0, 4, and 9, because x equals 9. So those are the four numbers we're going to be looking at. So let's go ahead and let's look at the shapes of the graphs. Okay. Well, the first thing we know is that we're going to be looking at the positive, we're going to be looking at the first quadrant. Because square root of x between 0 and 9 is always positive, and so is x over 2 between 0 and 9. So, first quadrant, x, y, 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow. Alright, so x equals 9. Square root of x, which is going to look kind of, sort of like that. And at 9 it would be 3. So I guess that's 3. I guess that's 2. I guess that's 1. 1, 1. Okay? And x over 2 is going to have a slope. It's going to be, let's see, a half, 1, 2. So they're going to have to intersect here at 4. Alright. This is where my lack of artistry is a real liability. Okay. So that's basically what the curve looks like. So we've got to figure out this area in here and this area out here. Well, what do we know? We know that in here, the top function is y equals square root of x. But out here, the top function, after 4, is y equals x over 2. So, as I mentioned last time, whenever you've got something like this, you want to put that as the sum of two different integrals, with the top function minus the bottom function plus another integral with the new top function minus the bottom function. So basically what we're asking for here is we're asking for the integral between 0 and 4. A equals the integral between 0 and 4 of square root of x minus x over 2 dx plus the integral between 4 and 9 of x over 2 minus square root of x dx. Well, let's go ahead and integrate them. That'll give us 2/3 x to the 3/2 minus x squared over 4 between 0 and 4, and x squared over 4 minus 2/3 x to the 3/2 between 4 and 9. Plugging in those values using the fundamental theorem of calculus, you'll get something like 16/3 minus 4 plus 81/4 minus 18 minus 4 minus 16/3. You'll notice that I omitted the minus 0 because when you plug 0 into that function, you get 0. And if you take the sums and differences of all of these things, as God is my witness, you will get 59/12. And that is the area between those two curves on the interval from 0 to 9. Now, today we're going to be expanding this idea of area into the notion of volume. Now, when we took areas, we would take rectangles. You remember that? We'd take a long series of rectangles, and we'd take the limit, the Riemann sum, we called it, the limit as the number of rectangles went to infinity of the area of all of those rectangles. Well, if we remember that, it's going to make the idea of volume seem pretty simple. Please bear with my awful artwork. Let's say we've got a sphere. I don't even really know how to make this look like a sphere. Maybe these are cross sections of the... God. Let's pretend that this isn't just a 2D circle. Let's flip this circle around the y-axis or around the x-axis, and we'll get an actual round object. But you see, thinking of it as a circle will actually help us. Because if this is a big round object, well, we know that when we take a curve, if we were to take the area of this circle, what would we do? Well, we might take rectangles of the circle. But if this is a sphere, how would you slice a sphere to take its area? Well, instead of slicing it into rectangles, when you cut a sphere, like cutting an orange, this is a good analogy. If you were to cut an orange down in between it, and then you split the orange in two, when you're looking at that orange, you're seeing a circle. And then you can slice it again and you'll see another circle. You'll slice it again and it's another circle. So basically, an orange is just the sum of all of those slices of orange that can form that sphere, right? Alright, well that's the idea of volume. Volume we can view as the limit as n approaches infinity of the Riemann sum, I equals 1, of a xi star delta x, or more simply, the integral between a and b of the area dx. This is pretty simple. And the only geometry you'll really need to know here are, well, the most important one is the area of a circle, because we're going to be dealing with cross sections that are slices. Area of a circle, as you know, pi r squared. So basically, we're going to be looking at some sort of variation of pi r squared. dr. But we're going to be looking at pi r squared variations throughout this section. So, let's see how this works. Let's see. Okay, we're going to find the solid. It's called a solid of revolution. When we take a graph and we rotate it, we're revolving it, creating something circular. So we're going to find the volume of the solid by rotating around the x-axis the curve y equals square root of x. Well, here is y equals square root of x, and we're going to flip it around the x-axis. So we're going to get this. But it's going to be spherical. So what we're going to do now is we're going to go ahead and we're going to make cross sections. Every time we make a cross section, we see a disc. We look at it, we take the graph, we flip it, we look at it like we did the orange, and we see a circle. And that circle has area pi r squared. So we know then that the area, or that the integral, is going to be between 0 and 1 ax dx. So between 0 and 1 we get pi, but we know that x, in this case pi r, the radius of that circle, is the function square root of x. We can see that because that's what it is. Basically it's going to be the value. If the function looks like this and we have a circle, alright, square root of x, actually negative square root of x. Well, the radius from here, which is the center point, the x-axis, the radius between there and the function is square root of x. It's square root of x here, it's square root of x here, it's square root of x here. Now square root of x always has a different value, but in general the radius is square root of x. So it's going to be square root of x squared, pi r squared, r being square root of x, and we get 0 to 1, take pi outside, x dx, forgot the dx, and we get pi x squared over times x squared over 2 between 1 and 0. So we get pi times x squared over 2, or times 1 squared over 2, which is 1, or pi over 2. You'll find that most answers here are going to feature the number pi. So there you go. That's one way to look at the area of revolution. Now we have another way. Sometimes you're not going to have a perfect circle that you're going to be dealing with. Sometimes it's going to be a little bit different. So like for instance, if we've got the curves y equals x and the curve y equals x squared, and we're going to flip about x. Alright? So let's look at this. Well, because we're going to be flipping, we know y equals x. We know y squared equals x. And we know that right here is the point 1, 1. Because that's where they intersect. You can check it, or you can just remember that that's where they're going to intersect. 1 equals 1 squared. So they intersect there. Okay, that's great. Let's flip that around the x-axis. And all of a sudden, we get something kind of weird. See? We got something weird now. Because this is a solid volume. But if we look at it, go ahead and picture this. Picture this graph right here with the two butterfly lips flipped around. If we look at it, are we going to see a circle? Not really. We can slice it here and we're going to see a circular object, yeah. But what about this missing space in here? And sure enough, there's going to be a hole in the middle. See? There's no values there. We've got this part, we've got this part, but we don't have that part. So there's a hole. So you've got to figure out the area of this thing. the donut-like thing called an annulus or a torus in math. So basically, we have this torus-type object, and it's pretty easy to figure out what this is because we know the area. We know how to figure out the integral and the volumes between areas now. So this is just the area of the upper minus the inner. Well, the inner function, I equals x squared. The outer function is x. So now what we're going to do is we're going to set this integral up. It's going to be between 0 and 1. Volume of that is going to be between 0 and 1 of the area, dx. Okay? Now we know that the area equals pi r squared dx. Okay? So volume is going to equal pi times r squared. Well, the area of those circles was x minus x squared. That quantity squared, you're going to end up getting x squared minus x to the fourth dx, which is the same, which when we integrate that, very simply, we get pi times x cubed over 3 minus x to the fifth over 5 between 1 and 0, which is just going to be a third minus a fifth times pi, which is 2 pi 15ths. Okay? It's as simple as that. You're just finding the circle, finding the cross-section's area, realizing that the radius is going to be that difference there, plugging it in, squaring it, and multiplying that integral times pi. That's how you solve the volume of a solid of revolution. Now, please note, sometimes, you'll get a function looks like this. Alright, this is y equals x squared, but revolved around the y-axis. We get a bowl, a paraboloid type thing. And with here, we can't really take circles, cross-section circles, along the edge of the bowl. We have to take them from the top, around the y-axis. Now, if we do that, it's going to be just like the area between curves. You're going to take x, y, and instead of doing a dx integral, you're going to do a dy integral. And the integral that you're going to be using y, dy. Things like that. Actually, I'm not sure if this is the best example, that function, but I can tell you that this is the general idea, that when you're doing a dy integral, that's the reason you do it, because you want to make the bowl slices go this way instead of this way. Yeah. Alright. So, that's all for volumes of the regular volumes. Next time we're going to go over another way to look at volumes, and that's the volumes by cylindrical shells, which is a lot different, but it's going to make it easier to find volumes of other things. By the way, just one other thing that the book points out that I'll just throw out there. You know the pyramid, the idea of a pyramid? If you want, you can do this. Take cross-sections of the pyramid. What's the cross-section of a pyramid going to be? It's going to be a square. Alright? Basically, what this is going to do is, if you've got a pyramid with x, here's your height, here's your base, x-axis, you're going to take squares along dy, good practice for that, and when you integrate, you'll end up with the volume of a pyramid equals L squared height over 3. That's just something that they point out in the book. They derive it. If you want to figure it out, feel free. That's how it's done. Now, on to the big problem for the night. I would like you to find the volume of the solid. X equals y squared, and x equals 1, and I want you to rotate that about the line x equals 1. Alright, that should be some good practice. Thanks for stopping by, and I'll see you next time. We've got 2 more lectures and 1 test left.